Hi everybody, my name is Scott Ellis and I'm here at UC Berkeley in an ultra-fast spectroscopy lab. I'm here to tell you about the work my lab has done writing custom instrumentation software in Python called pyFSRS. pyFSRS was originally written by Daniel Dietz and it's maintained by me. The beautiful thing about pyFSRS is how modular it is. So I encourage you to use it for integrating your own devices and for your own automation needs. pyFSRS has a few advantages over other software like LabVIEW. First of all, it's easily installed in 5 minutes. Secondly, there's no subscription fee, so you'll save your lab some money. Third, there are no updates, so your software won't break after about 5 years. And finally, writing code in Python is a transferable skill, so your workers will benefit in the long run. The next thing I want to show you is how we use pyFSRS to control our instrument, which is an ultra-fast laser detector. The laser gives a signal from a regenerative amplifier. The signal is a 5-volt TTL signal at 1 kHz. The signal from the regenerative amplifier is handled by a D-type flip-flop circuit. The D-type flip-flop handles the logic from the chopper driver and the regen to synchronize the pyFSRS CCD so that it triggers with the correct phase with respect to the set and reset signals. The signal from the regen is split on the D-type flip-flop and split again on the chopper driver using a split BNC port and is relayed to the lock-in amplifier. The lock-in amplifier reads out a fast photodiode at a carrier frequency of 1 kHz. The instrument uses a computer control simultaneously the signal from the lock-in amplifier, a pyFSRS CCD. The computer also controls a shutter via a shutter driver and an integrated BNC digital converter. Finally, the computer controls a translation stage via a nanomover motion controller. Real quickly, I want to show you how we install the pyFSRS software. The first thing you have to do is download the getpip package. Once you have that downloaded, you want to navigate to the folder where getpip is located and run python getpip.py. I've already done this. Then you should go to github/dd/pyFSRS and download the software pyFSRS. And once you have it downloaded, you're going to navigate to the folder where it's located. In this case, it's called pyFSRS-master. And we need to run the installer. So type in python pyFSRS-installer.py. I've already installed the installer, but what this will do is add the Python packages necessary to run pyFSRS. So those packages include pyvisa for interfacing with serial ports and other devices, and the wxPython package for building GUIs. Now we can run pyFSRS, so you type in python pyFSRS.py and it loads. Importantly, when you first install pyFSRS, you'll only have 4 instruments available. You'll have dummy axis, dummy camera, dummy DAC, and dummy shutter. These are virtual devices which aren't actually connected to anything. The difficulty arises when you have modules in devices, in installed devices here, which are not connected to your computer. pyFSRS will crash. So it's important when you first launch pyFSRS to only have 4 devices in installed modules. These are dummy axis, dummy camera, dummy DAC, and dummy shutter. Then when you want to add new devices, you navigate to available modules, and you can copy and paste these real devices into installed modules. So you move them from available modules to installed modules. Here first I'm showing you the shutter, and so when I click open, you can hear it click. Next I'm showing you the Newmark stage. So this is a motion controller which actually can control 3 different translation stages. Right now I want to select AY. I can control the speed of the stage, so it's a 10, and then I can move it to, let's say, -400,000 femtoseconds. You move it by clicking start. You can also generate a position log down below, and what this does is report where the stage is and at what time, so that if pyFSRS crashes, you can recover your time point, and so you don't lose time 0. Log path tells it where to save the log file. So here I'm going to click run, and you're going to see the translation stage move to negative 400,000 femtoseconds. There it goes. Here the pyFSRS 100 is the CCD camera, which again we're triggering from the regenerative amplifier and the shutter driver, or chopper driver. We can tell it how many frames to average. We can tell it how many pixels to read out, and you can flip the phase with respect to the triggering. SR830 is a lock-in amplifier from Princeton Instruments, and you tell it which channel to read out the photodiode on. You can change the sensitivity, so right now it's reading out 100 microvolts per picoamp, and you can tell it to average for 30 milliseconds. And then you have your dummy devices, dummy axis, dummy camera, dummy DAC. So here, DAC scan lets you read out the lock-in amplifier and move the translation stage to very quickly run a time point scan. I can sweep the delay stage from negative 500 femtoseconds to 2.5 picoseconds with 20 femtosecond time steps. We can sweep out linearly or logarithmically or from a text file. DAC stats is similar to DAC scan, except we're going to average over 100 different shots, not touch the translation stage, and we'll report on the variance. PHSRS is where the business is done. So PHSRS Focus lets you read out the pyFSRS CCD camera in a continuous fashion. Right now our camera isn't being triggered by the regenerative amplifier because it's off. So let's just look at dummy camera for now. Here we're going to tell it to average for 80 shots or 80 milliseconds. Here's the output. On the bottom you can see what would be the probe with the Raman pump off, and then this light trace would be the probe with the Raman pump on. And then the top trace in this case would be the negative log of the probe with the Raman pump on over the probe with the Raman pump off. And so this would let you tune up on your signal. PHSRS Acquire is similar, except we can average multiple sets and then save the output of each set to a text file. Here I'm running 800 shots, or 8,000 shots, so this should average for 8 seconds. And here's the result. We have much lower noise in our signal because we've averaged for longer. Next I want to show you PHSRS Scan, which puts everything together. So we can choose which camera we want to read out. Right now we'll read out dummy camera. We can choose if we want to read out a signal that's a PHSRS signal or transient absorption signal, which is just the negative log instead of the natural log. Or we can read out a differential transmission. We can tell it to average a certain number of frames. So here I'm going to tell it to average 200 shots. And then we can choose which camera we want to change, or which axis we want to sweep out. Here we're going to sweep out from negative 500 to 2500. Or we can load a text file, and I'll locate a text file here, test time points. Then I can also read out the lock-in every shot. And so what this would be used for is normalizing your laser. If you had an unstable laser, you could put the photodiode at a key point and then just make sure that your laser is being stable during the scan. Here I can tell it to run a base name of alpha 0. I can choose the output path, and I can So here we can see the translation stage is moving. First it goes to 0 time points, then negative 200,000 time points, and then negative 400,000 time points. And then back to T0. And when it's done, the shutter closes again. So here everything's working together. The final thing I want to show you is the output files, which are loaded. So here we have to navigate to where we save the output to. So here I saved it to pyFSRS master. So we navigate to that folder, and we see alpha 0 is at 0 time point, then M200,000 is minus 200,000 time, M400,000 is negative 400,000, alpha is the base name, and then 0 tells you which set it was. So if you were to sweep out multiple sweeps of the translation stage, you would go up from 0 to 1 to 2. Then we also have alpha reference. This is the output of the lock-in amplifier. So let's take a look at that. So here on the left we see the time point, and on the right we see the readout from the lock-in, which right now is just noise because it's not reading anything. And then also we generated this position log from the new mark stage. So we can open that, and you see on the left it gives the time, then it tells you which stage we're activating, and then it tells us what time point it went to. So if pyFSRS were for some reason to crash during this scan, we could get back to the time point that we want it to be at. So that's everything I wanted to show you in pyFSRS. Thanks for listening. And yeah, I just want to emphasize that this work was originally done by Daniel Dietz, and it's maintained by me. And yeah, thanks.